Hi guys, product review time today. Today we'll be looking at the ISO-Tech LCR-1701. The exact same model is also available in the LCR-1703. The only difference is it goes up to 100 kilohertz for testing components. This one only goes up to 10 kilohertz. This meter is actually manufactured by Appa. Appa are the original manufacturers. The equivalent LCR meter is the Appa 701, which is this one, and you also get the Appa 703, and they are also redistributed by GW Instek as the GW Instek 915 and 916 series. We'll be having a look at the manual as well. It's not that great, but it explains a couple of things around the theory, measuring parallel and series resistance for these components, as well as some other factors that we might go into if we have some time. And we'll also be measuring a collection of components. We've got some very high accuracy resistors here, a high accuracy capacitor, and a bunch of other components that we'll be measuring, some inductors and small value capacitors. Let's quickly have a look at the manual here. That's the test probe that you get with the bigger brother, as well as the power supply and of course the USB cable. It's got all sorts of sorting modes. You can actually use a reference component and then sort all the rest of your components according to a specific tolerance value. I think the same function is also available in the BK Precision LCR meter. I'm not sure how useful that is in everyday use, but I suppose if you've got a bin full of components and you want to sort them according to the tolerance values, then that's a function that you can use. There you can see battery life approximately 50 hours. And yes, auto power off after 10 minutes. The inductance accuracies, so you've got 0.2% plus 5 digits on the basic measurement ranges, and that seems to hold true for most of the frequencies that you are measuring. 0.2%, 0.2% again, and although the ranges shrink slightly in terms of accuracy. And here we have the capacitance accuracy values. Yeah, 0.2% again, 0.2%, 0.2% for the basic accuracy values. All of them plus 5 digits. But we'll have a look in real life what the accuracies are. Curious to see what the resistance accuracy is here. Yeah, again 0.2% on most of the basic ranges. I've got a few very high accuracy resistors that we'll attach to the meter and see how much the meter is really off. And there's just plain old DC resistance accuracies as well. And you can see all the way up to 200 mega ohm. The meter itself actually feels quite rugged, feels really solidly built. I don't have any issues with the build quality. Plastics feel really nice. It doesn't have any hollow sound or anything like that. It's a really solid unit. It's got this really nice rubbery holster. It comes with the two probes. This specific model, the 1701, comes with the short leads and of course a calibration bar for calibrating your terminal inputs over here. More about that later. And of course then the only other thing that I don't have a cable for, but yes, it's got a USB port at the top. We'll be having a close look at that when we take this meter apart. Let's quickly have a look at the battery compartment. Now this is actually quite interesting. I see they say it can be powered externally by a USB cable or AC adapter, DC 5 volts. Really very nice metal thread insert. 4 AA cells, 6 volts, which the manual states will last about 50 hours. All the screws are metal thread inserts. I really like that. There we go. There's a cable here that leads off to the USB connector. rather nice bit of shielding in there. There's the USB connector. We'll take a closer look at that just now. Yeah, that looks actually rather well constructed. Here's the little daughter board for the probes, and actually you can see they repeat this 4-wire measurement capability on this little daughter board as well. So you can actually see here's the current bearing poles, and they combine in the actual binding post, and these, or not binding post, the actual probe, and there's the sense wire leading off there, and that's actually just connected with a little header pin connector there. Okay, virtually no input protection, but of course this meter is not designed to measure any high voltages or anything like that. And I bet this is where the keyboard connects. It's a bit of a strange connector, probably to just easily test the keyboard interface. Here's the two battery terminals over here and here, and power supply section over there, and of course the main processor or measuring chip that seems to be driving the LCD, as well as doing a lot of the measurement. We'll take a closer look at this chip down here. I suspect that might be the ADC. We'll have a look at that just now. And let's just have a look here. There you can see the USB interface chip and the connector leading off to the external USB connector. And right at the top here, we've got the connectors for the what I'm assuming is the LED backlight for the LCD display. Now this is rather interesting. The PC board has the designation 703-1F on it. Now the 703 is the big brother of the 701, the Appa 701. So I'm wondering if this is actually exactly the same board, and maybe just software differentiates between the additional features of the 703. And there we have the Scilabs, that's the CP2102, and that of course is a USB to Uart Bridge, very simple and straightforward. And the HI24 LC04, that's a 4 kilobit I2C EEPROM, and that's probably where the calibration data is stored, and maybe also the feature set of the specific meter. And this is part of the power supply circuit. That's the 8542A. It looks like it's a dual rail-to-rail op-amp from Analog Devices. Well, so this was definitely not the ADC. It is in fact a free-blown LCR multimeter chipset. So this chip actually does all the work, and the specifications of this specific chip also mirror the specifications and the accuracy listed for this specific LCR meter to a T. So yeah, that chip there basically contains everything you'd need to build a fully fledged LCR meter. What's interesting is, of course, this chip also has the 100 kilohertz function already built in. Okay, this should lift right out. There's the little daughter board. Okay, yeah, as expected, the keyboard is actually a separate PC board. Not much going on there, but of course on the front here, the 3 terminals, and there's the keyboard connector, but also, of course, something that I forgot to mention, the light sensor. Now that basically just measures the light intensity, and of course turns on the backlight when the conditions call for it. And there's just the USB connector, nothing too exciting about that, but definitely not galvanically isolated by any stretch of the imagination. Okay, so here are the input terminals, and I actually rather like them. They seem to be of a very high quality construction. No issues with that. A very quick little mod. I just added in some press stick into that hole there because the little beeper on this meter is insanely loud. So let's do a quick power measurement here, just to see where it no longer functions and what the current draw is. Now you'll have to excuse the meter is floating a little bit because it doesn't have its back shielding on, but I'm going to stick in a 100 microfarad capacitor. There we go, so about 11.5 milliamps while measuring a 100 microfarad capacitor. Right, so let's turn down the voltage and see at which levels the battery indicator switch. There we go, 5.5 volts, 2 bars left. And there we go, at 5 volts, 1 bar left. Four and a half volts, 0 bars left, still measuring the same value. There we go, and at 4 volts, just below 4 volts, it indicates that the battery has gone flat and stops measuring. So yeah, that's 1 volt per cell, not too bad. I've switched the camera to manual exposure, so let's just have a look at the backlight. I'm going to switch off the overhead light. And there you can see that's actually really nice. The backlight actually works quite well. The display remains quite legible, and of course if we switch back the overhead light, there you go. Very nice, good implementation, I would say. So let's run through the most common modes of this meter. Turning it on, the 10K shows it's the 10 kilohertz version. Of course you also get the 100 kilohertz version. It starts up in the last setting that you used it in, which currently is the series capacitance mode. You can of course set it to parallel mode, back to series mode, and then also you can measure the D value, Q value, ESR, and the phase angle. And of course in parallel mode you get all those values, but you can also measure the parallel equivalent resistance. Right, back to series mode. Next is just resistance mode at a specific frequency. Of course the frequency you can set to 10 kilohertz, 100 hertz, 120 hertz, 1 kilohertz, and back to 10 kilohertz. And then it's just got a plain old DC resistance mode for measuring standard resistors. It can go all the way up to 200 mega ohms. And there's the inductance mode, currently in parallel mode. Of course you can switch it to series mode, and you've got all the old suspects: Q, ESR, phase angle, D value, and so forth. Here we're measuring a 100 microfarad capacitor. It's got basically two modes. It's a 20,000 count meter. It's got two modes, so you can keep it in 20,000 counts, or you can switch down to 2,000 counts. I'm not sure how useful that is necessarily. It doesn't improve the speed at all. And let's switch it back to 20,000 count mode. Right, hold button, the kind that I don't really like. It's just a holds whatever is on the display there. It's got a zero mode, so in other words you can zero or delta out the current reading,
and you can get an offset if you add additional components to what you have already measured.
Now I really don't mind the display on this unit at all. The contrast is quite good. I don't have any issues with that. It's got a very interesting, like a bar graph. The bar graph doesn't actually show you the value that you're measuring. It's not high speed or anything like that. It basically just shows you how far you are from full scale, right? So in this specific measurement, it's measuring 100 microfarad capacitor, it's showing 91.17 microfarads, but it can go up to 200 microfarads in this specific range. Okay, so that's why it's almost just short of half, or 50% of the full scale, which is a fairly interesting use of a bar graph. I'm not sure how useful that is, but anyway, there you are.
Right, so to calibrate the unit, basically take the shorting bar, plug it into the probes there, or where you would normally put the components, and click calibrate. First it actually asks you, first it asks you to do an open calibration. So yes, I'll just remove the shorting bar, press the calibration button, it runs through the calibration. Okay, and once it says pass, you press calibrate again. Then it says short, that's when you put the shorting bar in. Then press calibrate again. There we go, passed, and we can remove the shorting bar. Press calibrate. Right, then it defaults to this automatic mode. You can actually now, say for instance, go to capacitive mode. There's the parallel mode. There's serial capacitance. And you can see it's sitting at 0 picofarad. It's measuring D value now. You can switch to SR. It's not measuring any component at the moment. So let's plug something in and let it measure it.
Okay, you can see that it's on the picofarad scale. So here's I've got a 33 microfarad 16 volt capacitor here. It's an electrolytic. Let's plug it in. And there we go, 31.23 microfarads. You can also see it's measuring the SR at 0.85 ohms. So this capacitor looks to be good. Let's take a larger value capacitor. I've got a Siemens 1000 microfarad capacitor here. Yeah, that's not too bad. It's set to 1 kilohertz frequency at the moment. So let's just step through the various frequencies quickly. Over here I've got 10 kilohertz, which is the highest that this meter will go. Hang on a sec. Now you'll see it cannot measure 1000 microfarad at 10 kilohertz. Right, so we'll just step that down. 100 hertz. There we go. 942 microfarads. No problem with that. ESR of 0.1 ohm. This capacitor is doing well, thank you very much. Alright, I have here a Vishay 0.1 ohm resistor. Let's put that in the leads. There we go, that's 0.1 ohm or 100 milliohms. Basically spot on, but you'll see I've got the clamps right onto the edge or the ends of the resistor lead wires here. And let me just show you something about the accuracy of this meter. If I move these clamps to the center, or right to the resistor body, we're going to be excluding the resistance of the lead wires, and this meter can actually pick that up. Make sure you've got good contact. There we go, 0.097 or 97 milliohms. So it picked up that 3 milliohm difference in the lead wires. Okay, let's measure this 82 nanofarad capacitor. It's a high accuracy capacitor. That's quite spot on, 82 nanofarads at 1.4 ohms ESR. And we can actually bump up the frequency to 10 kilohertz, and that's
0.1617 ohms ESR. Of course, you can measure the ESR just by going straight to the resistance range. And what about inductance? Here I've got a 1 millihenry inductor. There we go, 0.97 millihenry. And let's just beef up the frequency there. That's at 1 kilohertz. 977 microhenries. And at 10 kilohertz, more or less the same. What's really nice, and something that I really enjoy, is the fact that it has the dual display, so you can measure your component and also have the ESR value, but it also measures other values. It measures the D, well, there's the angle, theta, measures the D value, and this is the reciprocal value Q. Here's a 6.8 nanofarad capacitor. Different frequency ranges, 100 Hz, 1 kilohertz, and back to 10 kilohertz. This is a 22 picofarad capacitor, typically used with Arduino crystals for the oscillation circuits. So yeah, this actually has a resolution of down to, what's that, picofarad, that's 10 femtofarad, 68 microhenry, 470 microhenry, and here we have a 4700 microfarad capacitor. (4,100 microfarads). Always good to get an idea of what the ESR is. And then we do, well, actually quite close to zero. It's you'll notice here you can't actually see, you know, you don't actually have too much resolution on the 100 Hz range. If you go up a step, let's say for instance 1 kilohertz, then the maximum it can measure is 2000 microfarads, right? But you can still measure the ESR by going to the resistance measurement scale. And there you have the ESR. You can even beef up the frequency to 10 kilohertz and measure the ESR at 10 kilohertz. So yes, 0.021 ohm. This capacitor is definitely still very good. And you can even measure the inductance of this transformer primary winding. This is the 220 volt winding of this transformer, 8.7 henries, half a kilo ohm ESR. And there we go, quite a difference at a different frequency. Okay, now I'm actually calibrating the meter by shorting these two posts with just effectively a piece of wire, and then we'll do some additional measurements just between these two posts. I've got a Vishay, what's that, a 0.01% 5 kilo ohm resistor in there. Let's have a look. Nicely done, 5 kilo ohms on the dot. If I put my finger on the resistor, there we go, you can see it's got a negative, or actually a positive temperature coefficient. So I've got it measuring a 33 microfarad capacitor here, and there you can see it's about 200, well, this is at 100 Hz, so it's about 200 millivolts AC there. And so let's just bump up the frequency here, 120 Hz. Drops down to about 172 millivolts, and at 1 kilohertz we're at about 21 millivolts. So no problems if you're measuring in-circuit devices here. At 10 kilohertz, of course, the Fluke only has a bandwidth of 1 kilohertz. So let's put it on the scope and see what the 10 kilohertz peak-to-peak voltage is like. Okay, and then we've got it about 80 millivolts peak-to-peak with just over 80 millivolts DC offset at 10 kilohertz. Alright folks, I think that's it for now. I actually really like this meter. I think it offers excellent value for money.
I got it about $180 for the 10 kilohertz version. The 100 kilohertz version is about $20 more, for $200 more or less, from RS Components. Not sure if you can source them cheaper elsewhere, maybe for the Appa or the GW Instek. I actually have no idea what the pricing on that is. So yeah, if you really like this video, please remember to give it a nice thumbs up. That always helps, and I appreciate the feedback that you guys can give me. Thank you very much.